So welcome everyone for today's academic seminar. We thank you very much for joining the J-MENA events and activities. Today we are starting another academic seminar with Dr. Fatih Ozaydin from the Institute for International Strategy, Tokyo International University. I'm Khawla from the J-MENA project, and first I would like to introduce briefly the future or the upcoming academic seminars like today. Therefore, I would like to share the screen, and Sensei, would you please stop sharing the screen? So here, like today, we are having these academic seminar regarding computer science, quantum computers, internet, and blockchain. Also, we are glad to announce the upcoming academic seminars. So the next Thursday, we are having another academic seminar about renewable energy for electricity, potable water, and chemicals. So if you're interested in this field, do not miss this opportunity to learn more about this topic. Also, starting from October, we are planning to have more and more academic seminars about the cell biology and other research fields. So do not miss this opportunity as well. And we are also glad to announce that next week, Tuesday, we're having another session with the Begin Fair activities. So do not miss the opportunity to meet representatives from the Kyoto University of Advanced Science, known as KUAS, also Kobe Institute of Computing, as well as Osaka University. So here in the J-MENA project, we aim to introduce to all the students the different opportunities, how to study in Japanese universities, and how to apply for any program you would like to. Also, we are happy and a little bit sad that the Study in Japan fair is done. And many of you have asked us about the recorded meetings. We know that due to the time zone difference, some of you could not reach us live. So we are glad to let you know that you can join us in the YouTube channel of the J-MENA project, and all the recorded videos are uploaded now. So you can watch them more than one time, and you can learn more about the different programs offered at Japanese universities. Also, those who are new for the J-MENA project, you can reach us through the SNS platforms on Instagram, on Facebook, as well as on Twitter. We are aiming to introduce the general life conditions in Japan for you as a student. So do not hesitate to join us through all these platforms, as well as through email. That's all from me, and I wish that was helpful for most of you. And now we can move to the lecture with Fatih Sensei. The stage is yours, Sensei. Thank you very much.
Thank you very much, Kaola-san. So let me share my screen. Okay, today I'm going to talk about quantum computers, internet, and blockchain. Whenever you have any questions, you can just type in the group chat, or you can just unmute your microphone and ask me immediately. Please do not hesitate, okay? So let me first briefly introduce who I am, and then I will continue with the quantum technologies. So I'm from Turkey, and I was born in Antalya in the Mediterranean coast. I was raised there, and then I moved to Istanbul for the university. And I studied computer science in the undergrad program. And that time in my first year, I became interested in quantum computation. So that time, it was year 99, and quantum computation was not this popular actually. So I became interested in it, and I said, in order to do research in this field, I have to study physics, and basically quantum physics, which I was in love since my childhood. So I started my double minor in physics. Then I studied electronics engineering in my master's program. And before going to the PhD, I wanted to have some engineering experience. So I joined a company, a software company of Thales Group, Netherlands company, in a military project. And I developed middleware software for the project. Then I got a mixed scholarship, and I moved to Japan. After Japanese school and research studentship, I continued my PhD, and I obtained my PhD from Osaka University. My thesis was in quantum communication, and in particular, the quantum channel capacity. I have been to the McGill University to conduct research, and then I went back to Turkey, and I worked there in one university, in Okan University. I taught mostly computer and electronics related courses. Then I was invited to my university where I studied as a student, this time as an assistant professor. And there in the Department of Information Technologies, I taught several courses. And I worked at Washington University in St. Louis as a visiting professor. And I also served as the vice director of the Technology Transfer Office. And since 2016, I'm an official research collaborator of CERN. And then I was promoted to associate professor position in 2015. And then in 2017, I was invited to the University of Tokyo, the Photon Science Center, as a visiting professor for a one-year position. And I also worked as the manager of IT departments of an international Japanese company. Then in 2019, I joined Tokyo International University. And since last spring, I have been working there as a full professor. Okay, and because of my relations following my research in CERN, the Tokyo International University became the third official partner from Japan of CERN. So there are only three, and TIU is the third of them. I also conducted several freelance projects like recruiting platforms, table reservation platforms, etc. And I conducted and I worked as a researcher in several projects, including European Union projects on quantum space applications for developing quantum fuels for space applications. And I've been publishing my research mostly in Physical Review A, Nature Scientific Reports, and Chemical Society of America or Optical Society of America. You can check out my Google Scholar profile. Just search my name on Google Scholar, and you can find my recent articles and my international collaborators. My ongoing research activities are in quantum computation, quantum artificial intelligence and machine learning, quantum networks, and internet. I recently started working in quantum blockchains, and I'm doing research in graph-based quantum learning and self-learning and expanding networks. And my ultimate goal is to unveil the mysteries of quantum biologies and the quantum origins of life. So what are quantum technologies? Let me first summarize the recent advances. I'm going to show a few recent advances. Well, this one is not that recent, but this experiment is a milestone in quantum technologies because previously it was discovered by Shor that a quantum algorithm can perform the factorization, can solve the factorization problem in a very efficient way, much faster than the classical computers. And that theory was fun. And the first experiment, like demonstrating it, was in 2001, so almost like 22 years ago. And I can say that this experiment accelerated everything in quantum technologies. And one recent example from 2019 is that the quantum supremacy, which means, okay, take the fastest electronic computer, classical electronic computer in the world, and take a quantum computer, compare their performances. If the quantum computer can perform much better, if it can solve a problem faster than the fastest classical computer in the world, we say that is the quantum supremacy, and it was experimentally demonstrated. So that quantum computer at time had only 53 quantum bits, but it required only 200 seconds to solve the problem. But the state-of-art classical computer, the fastest in the world, would require about 10,000 years. Okay, so the quantum computers are like are in the years like 50s or 60s or the of the classical computers. Okay, so right now the quantum computers are so expensive. They're like they're as big as a room. Okay, just like the classical computers were in back in 50s and 60s. But now the technology is advancing, and IBM unleashed the quantum processor, which they claimed to be the most powerful quantum processor. And there are various other quantum computers working in different styles, like following different architectures, where you can just purchase and start using. Actually, NASA and Google was working, they were working on some quantum artificial intelligence problems using this quantum computer of the D-Wave company. IBM even opened its quantum computers around the world to the public over cloud. Now anyone can register and make a reservation all for free and can test his or her quantum algorithms on an actual running physical quantum computer. So there were several quantum computers around the world open to public, and now the most recent one is being built in Tokyo. So it will be, so there were some practical applications. So I think it started to work already. And quantum key distribution, like this is more technical phrasing, this is more accurate phrasing, I can say quantum cryptography. So in Tokyo, there has been a quantum network between Otemachi, Kogane, Fuchu, and Chofu doing communication, and the information is encrypted in quantum cryptography. Okay, so this has been working since 2010. The project was ready. Now, for the quantum communication and quantum cryptography protocols, most of the time a quantum computer is not required. Some experimental like lab devices are sufficient to perform communication and cryptography. That's why back in 2010, the quantum communication network with quantum cryptography system was already operational. So we can categorize the advantages of quantum technologies as two, like first is just an increase in the speed or the storage capacity. Okay, so these quantum computers can solve the problems which the classical computers can solve as well, but quantum computers much faster. Okay, and in the second category, we have the tasks which are impossible to realize by classical computers, but quantum computers can realize those tasks. Okay, so quantum technologies enable otherwise impossible tasks. Okay, so I put this word just in quotation marks because it's not a small increase, it's a huge increase, but still it's an increase. Okay, and I'm going to say a few words about what this incredible what this small increase results in, like incredible changes. Okay, so just as an increase in speed or storage capacity, for example, in the simple processing power. Okay, let's take an unsorted database consisting of n entities. For example, you enter, the professor enters the classroom and there are n students, and they are not seated in alphabetical order of their names. They are just randomly seated, and the professor is looking for one student, asking each student one by one, are you this student? If no, are you him? Are you him? Are you him? Are you him? So on the average, he will find the students in n over 2 attempts, but in the worst case, n attempts. So if there are n entities in an unsorted database, you would require n attempts, one by one. You should ask, are you that student? If no, are you that? Are you that? Are you that? So this is how the classical computers can find an entity in an unsorted database. N entities require n steps, but in quantum computers, only square root of n steps is sufficient to find what you are looking for. Let's say there are 10,000 items in your database. Classical computer is going to find it in 10,000 steps, but quantum computer is going to find it in 100 steps. Okay, just imagine how many entities, how many items there are in the databases of Google, billions of items, but moving that data to quantum computer, square root of that number will be sufficient. So this is an incredible speed up in searching in an unsorted database. The next task that classical computer can do as well, but quantum computer is much faster, is the Fourier transformation, which we have in every device in communication, engineering, and everywhere. Like all the electronic devices realize Fourier transformation always. And the other problem is the factorization. Okay, factorization is an interesting problem because it's different than multiplication, different than subtraction or addition. Take two numbers, each of 2 digits, for example, add them, okay, perform summation. Let's say you can do summation like 1 digit in 1 second. So 2-digit numbers, adding 2-digit numbers is going to take your 2 seconds. Adding like 20-digit number with a 20-digit number is going to take your 20 seconds, okay? 1 second per digit. So that is like, there is a proportional scaling. If 100-digit number by 100-digit number, and it will take your 100 seconds, okay? But factorization is not like that. Factorization is a difficult problem for us, for humans, because a 2-digit number like 15, for example, we can easily factorize it. Okay, 3 times 5, okay, only 2 seconds maybe. But a 3-digit number would require not 3 seconds, but longer to factorize. Okay, if I ask you to factorize 178, for example, or 179, let's make it more difficult. It's not going to take 3 seconds, it's going to take longer. Okay, and if I give you a number of 10 digits, it's not going to take 10 seconds, but maybe 10 minutes. Okay, so the time required to solve the problem scales not linearly with respect to the size of the problem. So because we don't have any algorithm, we don't have any method to solve this problem, so we cannot teach how to solve this problem efficiently to our computers. Therefore, factorization is a challenging problem for the computers. It takes a lot of time to solve it, okay? And therefore, the information security is based on the difficulty of this problem. Because it takes too much time, this factorization problem is embedded into the encryption protocols. So in order for a hacker to break our encryption, that hacker should factorize a very large number in a very short time. But it is impossible with the state-of-art computers. It requires like several thousand years to hack a current cryptography, because factorization problem, that encryption protocol is based on the difficulty of factorization problem. So with a normal computer or with a supercomputer, it takes just too much time, but a quantum computer can easily factorize. For quantum computer, factorization is not a difficult problem, but it's an easy problem, okay? And also image processing or computer vision, artificial intelligence, natural language processing, speech recognition, such problems are realizable on classical computers as well, but they are too slow because these are all challenging tasks. But quantum computers can solve these problems in a very efficient way. Regarding the storage, if we have n classical bits, one such a string can represent one of the possible n-bit strings. Like if you have 2 bits, it can represent either 0, 0, or 0, 1, or 1, 0, or 1, 1, okay? If it is like 10-digit string, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, or the other, or the other, or the other. So there are 2 to power n possible bit strings, but a classical computer can represent only one of them at a time. But a quantum computer can represent all of those entities at the same time, because each quantum bit can be logic 0 bit, or logic 1 bit, or the superposition of being both 0 and 1, okay? And because each bit can be both 0 and 1 at the same time, all those 2 to possible n possible 2 to power n entities can be represented simultaneously. Therefore, it's going to result in a revolution in storage and especially in processing big data. Okay. So this is about how the factorization problem can be solved in a quantum computer very fast. Okay, and just recently there was a report in MIT's technology review showing that a quantum computer could break a very powerful, a very strong encryption protocol only in 8 hours. So it would take like thousands of years with classical computers. So all the classical encryption protocols can be hacked, but the point is that they require just too much time, thousands of years, hundreds of thousands of years. That's why we say, okay, this encryption protocol is secure because the enemy or the hacker would require hundreds of thousands of years, but a quantum computer can easily hack it. Therefore, all the information security is at stake because the quantum technology poses a real threat to the information security. Okay, and like some of the recent works I have been doing is in quantum key distribution and quantum communication and networks, and also the quantum teleportation. I have some slides on quantum teleportation. I will show that it's not a science fiction. Like teleportation is a science fiction in classical technology, in classical world, but not in quantum world. Okay, so I will present a few results on the predictions on the financial services, because not everyone here are meant to be like engineers or physical scientists, but maybe like finance people or economics people. So IBM has been releasing reports for exploring the quantum computing use cases for financial services. So this is from the IBM's report. So they take a problem just like the factorization problem or some artificial intelligence problem, which scales exponential for the classical problems. The time requirements to solve the problem scales exponential with respect to the size of the problem. Okay, but in quantum computers, it scales only polynomially. Okay, so if the same problem but small size, like creating our machine learning trained profiles for our clients. Okay, if you take a few clients and a few parameters for the training set, it takes 10 seconds for a classical computer to solve the problem. 1 minute for a quantum computer, because at first it starts like slower. But when the size of the problem grows a little bit, it requires 2 minutes for the classical computers and the same for a quantum computer. But if you further grow the problem a little bit more, it's like 5 times bigger, okay? So 5 times more people or 5 times more parameter in the training set, then it would require 5 times more in a quantum computer, not 2 minutes, but 10 minutes. But the time requirement for the classical computer decreases from 2 minutes to more than 3 centuries. Okay, if you further make the problem bigger, then it would take 3,300 years for the classical computer, but only 11 minutes for a quantum computer. And if you further grow the problem, it would require the classical computer to solve the problem as like 15 billion years, but only like 25, 24 minutes on a quantum computer. So this shows that the quantum computers or quantum technologies in general are going to enable a lot of things in financial services as well. Okay. So right now we are here, okay? This blue bold curve is for the quantum computing's capabilities, and this purple one is the capabilities of the classical computers. Right now, the classical computers are better than the quantum computers in most of the tasks, but soon the quantum computers will be as capable as classical computers. But then, because the classical computer technology is advancing linearly, but quantum computing technology advances exponentially, soon in 1 decade or so, the capabilities of quantum computers will be much richer than the classical computer, and this gap will keep expanding. Okay, so financial services are predicted by IBM to profit for about $1 billion if quantum computers are used in banks or financial institutions. In some problems like feature selection or product recommendations, the expected revenue is around $1 billion. In some other tasks, between $1 and $5 billion, and in bigger problems like fraud detection and forecasting financial crashes, the expected benefit is greater than $5 billion. Okay, that's why financial institutions which become aware of these potentials of quantum computers start to invest incredible amounts of money to this field. And I will present some solid evidences for these quantum computing advantages. That this article was published recently in the top journal Nature. They say here we propose an experimentally implement 2 quantum algorithms on a superconducting processor. Both methods use the quantum state space as feature space. The use of a quantum enhanced feature space that is only efficiently accessible on a quantum computer provides a possible path to quantum advantage. So in this experiments, they have proven the quantum advantage. And another research recently published again. So it proved the quantum advantage in variational optimization. And another one, again recently published, shows the quantum advantage in quantum risk analysis. So for risk analysis, we develop and run simulations based on random variables, which we call Monte Carlo simulations. And they say we present a quantum algorithm that analyzes risks more efficiently than Monte Carlo simulations traditionally used on classical computers. So these are all experimental demonstrations, okay, proving the quantum advantages. And quantum technologies are expected to provide incredible advantages in the battlefield as well, or more general in the defense and security. So you can check out the reviews published by NATO or Thales, the company I worked for between my master's and PhD. So they have formed teams, researcher teams, to catch the quantum revolution, and most of them working on quantum sensors, communications, and post-quantum cryptography. And another report is this. You can just take this screenshot, or at a later time pause the video and read this one. Okay, this is a report from the Congress, from the United States Congress. So I can recommend a very recent review article on quantum technology for military applications. So this is not a very technical article, so I think everyone can read it, especially if you are interested in the defense electronics. So quantum technologies can be used as quantum cyber warfare, in quantum internet, quantum computer, and quantum radars, quantum sensors, quantum electronic warfare, chemical detections, radars, underwater warfare, navigation, mapping. So there are various types of technologies that can benefit greatly from the quantum revolution. Okay, so what is quantum mechanics, and why do we need quantum mechanics? Like, what is this quantum? Okay, the common example, well, I have taken these screenshots from a popular YouTube video called Dr. Quantum, an animation video. It is explained very well there. So if you take some paintball guns and shoot to a screen, but there is another screen in between, if there is a single slit here, the balls on which can pass through this screen will hit the screen, the other screen in the back. Okay, so if you have 2 slits here in the screen below, then some balls will pass through this slit, some balls will pass through this slit, the right slit. Therefore, there will be traces, there will be some paint behind on that wall as this trace and this one. Okay, so this is intuitive, right? This is what happens if you take a paintball gun and start shooting. If you repeat the same experiment, this time in water waves, like you put this and you just send a wave, okay? This wave passes through both slits, okay? And then there appears here the interference of the wave with itself. So the wave interferes with itself because the same wave penetrates through both of the slits, okay? So particles behave like this. Each particle can pass through only one slit, but waves pass through both slits, okay? What happens if we repeat the experiment, this time with quantum particles, like electrons, for example, okay? Take an electron gun and just start shooting to the wall through a double slit screen, just the same screen, okay? But this time, what we see on the wall as a trace of these electrons is the same with the result of the wave experiment, okay? So this shows that the particles, if they are very small, if they are in the atomic scale, they behave like waves. So they are particles, but they also behave like waves. And so we call it the particle wave duality. And depending on the setup of the experiment, either the wave behavior or the particle behavior is observed, okay? So one interesting thing here is that if you shoot a single electron, you observe the same pattern here, the same interference pattern here, which shows that the single particle passes through both slits, okay? So you shoot one electron, it passes through the slit on the left and the slit on the right at the same time, okay? So this sentence is not 100% accurate in quantum mechanics. I should say, more technical phrasing, I should say, the particle exhibits the superposition of two wave functions, each wave function corresponding to passing through one slit, okay? But rephrasing it, it passes through both slits, okay, at the same time. One interesting thing about quantum world is that if you don't look, if you don't observe through which slit the electron is passing through, you observe the expected wave behavior, the quantum wave behavior. But if you put a camera there, if you interact with the system to check out through which slit it really passes through, what you see is the classical result. So here the wave result is taken, and here the particle result is obtained, okay? So the measurement changes the quantum setting entirely, okay? So in order to explain this phenomenon to the people, one of the fathers of quantum mechanics named Schrödinger considered an example where there is a cat in a box and there is a radioactive so he devised this thought experiment where we put a cat into a box and there is a radioactive element in the box. If the radioactive element decays, it's going to trigger a mechanism which kills the cat, okay? So because this is a quantum mechanical process, the decay of the radioactive material, it's like it decayed and it did not decay, okay? Just like passing through both slits. It passed through this slit and it passed through the other slit at the same time. So this radioactive atom has decayed or it has not decayed. Therefore, it triggered the mechanism and it has not triggered the mechanism. Therefore, it killed the cat and it has not killed the cat at the same time. Therefore, the quantum of the cat is both alive and dead, okay? He also, in order to explain the impact of the measurements on the quantum systems, he said, okay, let's connect this mechanism to the box so that if you want to open the box, the same mechanism will be triggered and the superposition quantum state of the cat is destroyed. The cat is found dead, or okay, or when you open the box, you will find it alive or you will find it dead. So the quantum mechanical information is destroyed, and we are left with the classical information. Okay. So, okay, let's dig into more technical details. A quantum bit can be 0, can be 1, and can be both, it can be in the superposition of being 0 and 1 at the same time. Okay. So if we imagine a three-dimensional sphere, okay, and one point on the sphere representing the classical 0 bits, and this point, okay, in the bottom, represents the classical 1 bit. So in this three-dimensional shape, we have the surface of the sphere. We have infinitely many points on the surface, but only 2 of them are the bits that we use in the classical world. But in quantum world, we have access to every single point on the surface, which means that we have infinitely many representations of bits. We are not limited to 0 and 1 only. We have any value of superposition of being 0 and 1. Okay. So this is called the superposition. And this is a consequence. We don't know how exactly it happens. So there are mysteries in superposition and entanglements we are hoping to solve. But so like we do the experiment, we go to lab, we do the experiment, and we observe this. Okay. And as an engineer, I'm using this for building up quantum technologies. Okay. Just like to use a smartphone, you don't have to be an electronics engineer. You don't have to know how it was designed and manufactured and how the software is developed, right? You just need to know how to use it, okay? So besides the mysteries of entanglement and superposition, we observe it, we can manipulate it, so we can build technology on top of that, okay? So this is a concept, but what we know is that this is a consequence of the wave behavior of quantum particles. We have one wave, we have another wave. These waves can be in superposition, right? 2 waves can be interfering, going on top of each other, okay? So waves can have superpositions, and quantum particles are waves as well, therefore they can have superpositions. And the entanglement is a more interesting and maybe the more difficult to understand concept. So let's say we have 2 or more particles, and each particle is in a superposition of being 0 and 1, but sometimes 2 or more particles are entangled with each other, or more technical phrasing, their wave functions are entangled with each other. So that if I measure one particle and find in 0 state, the other particle will be found in 0 state. If I find in 1 state, logic 1 bit, the other will be found in the same state, okay? So this is an entanglement. We don't know exactly what entanglement is, but we know what it is not. It is not a classical correlation. In classical physics, we don't have such a correlation, okay? So in more detail, a classical bit can be either 0 or 1. It cannot be both 0 and 1 at the same time, okay? It can be either 0 or 1. So in the three-dimensional illustration, a classical bit can be represented by a vector pointing to this point or a vector pointing to this point. So we have only 2 vectors because we have only 2 points on the surface of the sphere, the three-dimensional sphere. But a quantum bit can be in the superposition of being both 0 and 1. And these are the superposition coefficients, okay? So if I measure this, if I measure the state of this quantum bit with the square of with the square of this probability, with the probability being equal to the square of this parameter, I'm going to find this quantum particle in the classical 0 state, and with the probability beta square, I'm going to find it in classical 1 state. Okay, so measuring or performing a complete measurement on a quantum system kills the quantumness. We lose all the superposition and all the entanglement, and we are left with the classical state. So we need to design and run our algorithms before the measurement. Okay, as long as each bit is both 0 and 1. So this introduces the advantage because each bit can be both 0 and 1 at the same time. Let's recall the factorization problem. In classical computers, the only thing we can do is to check whether this target number is divisible by 2, by 3, by 4, by 5, by 6, 7, 8. Well, we can skip some of them. We can skip the even numbers if it is not divisible by 2. So we can do some optimizations. But the only thing we can do is to check the numbers one by one. By this, by this. Is it divisible by 11? Is it divisible by 13, by 19, by 31, etc. But the quantum computer, well, I'm a little bit like making it like a cartoon. This is not very technically accurate, but just to give the idea, thanks to the superposition principle, a quantum computer can check all the possible solutions in one step. Okay, therefore it is speeded up like crazy. So how can we have the superposition in physics? Okay, on the paper it looks fine. So we have developed mathematics for it, axioms for it. Okay, but what about the physical life really? So if you take a single photon, okay, not a light bunch, okay, so an ordinary light bulb is emitting about 20 trillion photons every second, okay, but like in 1 second 20 trillion photons, so too many. Take only one of them. So if you take only one of them, you can access to its quantum mechanical properties. And photons, the light particles, have polarization. And that's why we have some polarizing some sunglasses, right? So each photon can have the vertical or horizontal polarization, okay? And we can label the horizontal polarization as logic 0 bit and the vertical polarization as logic 1 bit. And the interesting thing about a single photon's polarization that its polarization can be horizontal or vertical, or the superposition of being both horizontal and vertical, okay? Or if you take a single electron, we have the magnetic properties of the electrons, what we call the spin, okay? The electron's spin is binary. It's either up or down, okay? But it can be also in the superposition of being up and down at the same time. Just think about a magnet, okay? The magnet has two poles, south and north. Just think that it has the quantum magnet has one pole in both south and north at the same time, okay? Or take a single atom. If the atom is in its lowest energy state, so it has not absorbed any photons, okay, it's cooled down and it emitted all the photons and it is in its lowest state. And if it, so we call it the ground level or the ground state. If it absorbs some electron and its energy is increased, then we call it the excited energy level, okay? So we can use this as a binary information. G for 0, I think you can see. Okay, so the energy of a single atom can be the lowest energy or the excited energy, and the superposition of being the ground and the excited. Because a photon can be absorbed and not absorbed by the atom, okay? If not absorbed, the atom is in its ground level, ground state. If it absorbs the photon, it is in the excited energy state because it can be both absorbed and not absorb the photon. It is in the ground and excited energy states. Okay, so physically we can observe all these superpositions and entanglement in the lab. Okay, so let me say a few more words about the entanglement. Okay, let's say we have two parties, Alice and Bob, and each particle possessed by Alice and Bob are in superposition, but these superpositions are entangled to each other. So now we can write their state mathematically as, so the first bit belongs to Alice and it is both 0 here. I will show that in like, what is this color? Orange. So the first bit belongs to Alice as the index shows. It is both 0 and 1. The same for the particle of Bob. Bob's particle or Bob's qubit is both 0 and 1, okay? But these are entangled to each other. Whoever measures his or her qubit first will find the particle in 0 or 1 state with 50% probability, okay? So if you, let's say I and you share one particle each, okay? We have a pair of particles. I keep one, I generate 2 particles, I entangled them, I keep one to myself and send the other to you, okay? If I measure first, I will find it in 0 or 1. I will find it as 0 classical bit or 1 classical bit with 50% probability. But after my measurement, if you measure, you're going to find exactly what I found. But if you measured before me, you will find 0 or 1 with 50% probability. So you have a freedom there. You will find either 0 or 1. You have a chance to find it in 0 or 1 state because you are measuring the first. And after your measurement, if I measure, then I will find exactly what you found, okay? So let's say we have really shared such a pair of particles, and I'm here in Japan, you are in another country, let's say, okay? I measure my particle, I learn its state, okay, it is 0. Let's say I found 0. That moment, I happen to know that your particle will be found in as 0, okay? Whenever you measure, you're going to find 0. But if I found 1, you will find 1 for sure, okay? So having shared a pair of quantum particles, now it's like we have opened a quantum channel. We have opened a gate to quantum world, okay? So we have a quantum channel, and without communicating, I know what you are going to find, okay? And you know what I'm going to find. Therefore, we don't need further communication, okay? We already know what the other party will know. This is impossible in classical information. In classical, you have either 0 or 1, and you know what it is. You cannot have this, okay? So in classical computation, we have the logic operations, realizing the aristologic, because each bit is either 0 or 1. So this follows the logic of Aristo. So we first start with a proposition. The truth value of the proposition is either true or false, but not at the same time, not true and false at the same time. So this is the very basic definition of the proposition in classical logic. But now we have something different. We have a bit which can be both 0 and 1 at the same time, so both true and false at the same time. Therefore, now we have the quantum logic. So all the classical information computation technology was based on the classical aristologic, but now we have the quantum technology based on the quantum logic. Okay, so we have the quantum logic operations, just like the classical logic operations, we have the quantum logic operations in quantum computers. Okay, and this is an experimental setup by, so this is a photonic quantum computer. We have the laser here. This laser generates single photons, and we have optical elements, some crystals, some optical elements, some mirrors, prisms, okay? Because this laser emits a single photon, all these optical devices manipulate the quantum state of the photon, can create superposition, entanglement, okay? Can manipulate the quantum state of the single photon, okay? So this is the illustration of a real experiment. Okay, maybe I should skip this quantum computation example because we're running out of time. So quantum teleportation. Okay, in classical world, maybe you remember from the Star Trek, like beam me up, Scotty. So they have the teleportation there, which is impossible in classical technology, but it's possible in quantum technology. Let's say Alice and Bob have previously shared a pair of quantum particles, this particle and this particle, okay? And then one party, another party gives a particle to Alice and says, hey, Alice, could you please teleport this particle to Bob? But Alice doesn't know the quantum state of that particle, okay? If Alice knows, then just call Bob and say, prepare the same particle on your side. But here, the brilliant thing about quantum teleportation is the ability to teleport an unknown state of a quantum bit, okay? So Alice performs a measurement on her side with that particle and her particle, and measures those two particles, and through a classical channel, for example, telephone or SMS, she informs Bob about the result of these measurements, M1 and M2 measurements, and Bob applies some quantum logic operations on his qubit, and the resulting qubit will be exactly the same qubit that Alice was given by Charlie in the first place. So this qubit has not been transported to Bob's side. Maybe Alice is in the world, Bob is on Mars, okay? So this particle is not transported, is not transferred from one place to another. It is actually measured and it is destroyed, but its quantum state is teleported from one location to another location, okay? Okay, maybe I should just continue and finish and then try to answer your questions. Otherwise, if we continue with questions on quantum, we might not have any time on quantum blockchains. So first, let's visit the basics of blockchain technology. So we have the transfers, we have the assets, and time to time we transfer our assets, like make a bank transfer, and we need to record these transfers. Like traditionally, the ledger, which is the record of the transactions, were centralized. The bank keeps a single and legitimate copy of your transaction records. Well, you might be given, so this is the central ledger, which is the only legitimate ledger. Only this ledger is considered as a fact, okay? The clients can keep copies of it, but none of them is legitimate. Okay, none of them is acceptable when you go to the bank. Whatever it writes on your bank notebook, it doesn't mean anything when you bring it to the bank. The bank treats only its records as legitimate. Okay, so it is easy to maintain such a centralized ledger. The banks keep a single copy, protects it well. Okay, no problem. But the motivation behind the blockchain technology is to decentralize whatever out there is, starting from the currency, okay, starting from the money and various applications. So they say, okay, let's take the power and control of the government on the currency and other applications, and let's not require any central authority to have the system work, okay? And let's distribute the ledger to every individual in the network. Here, the copy of the ledger held by every single individual, every single peer of this network is a legitimate copy. But it is problematic how to maintain its security, right? What if someone changes it? So it requires some technology, some cryptography, and some efforts, the mining efforts, okay? So the traditional records of transfer of assets were centralized. So this is still what we have in our banks, bank accounts, and everything else. And the idea of blockchain is to distribute this ledger, okay? And how come it can be secure? Okay, so in order to add a new block to the chain, we call it blockchain because it consists of blocks in a chain, okay? So when there are some transactions, like Bitcoin transactions, the Bitcoin miners assemble a new block with the transactions in the waiting list. And in order to add this block to the chain, to connect it, to link it to the last block in the chain, some mathematical problem should be solved, okay? And that requires effort. That requires mining kits, okay? It's a very difficult problem to solve. It's like we call it puzzle, okay? And to solve that puzzle is demanding. In the first years of Bitcoin, you could solve it with your ordinary computer, but then it required graphical processor cards, and then more special mining kits like FPGA, and now ASICs, and even the ASICs cannot solve this problem. Okay, so solving the problem is required to add one new block to the chain. And the Bitcoin is secure because, let's say a hacker comes and wants to alter the transaction in block 74. So block 74 says, Alice sent 5 coins to Bob, okay? Now these 5 coins belong to Bob. But the eavesdropper comes and erases that data, okay? And writes there his own name. Alice sent 5 coins to Charlie, to me, okay? But doing that, the link between block number 74 and 75 is broken because solving that puzzle is based on the contents of that block. If you alter the contents of that block, it is not linked to the next block anymore. So the chain is broken. Okay. What the eavesdropper should do is to solve the puzzle for block number 75 so that it can be linked to 74. But solving the puzzle for 75 modifies its contents. Therefore, the link from 76 to 74 is broken now. So the hacker should solve the puzzle for block 76 so that it could be linked back to 75. But solving the puzzle modifies its contents. Therefore, the link from 77 to 76 is now broken. So this way, the hacker should solve the puzzle for block 74, for 75, 76, 77, blah, 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 up to 90 and 91. While the entire mining network with all their mining kits are working on a single block, the hacker should, so all the mining network, everyone is working on solving one puzzle, but the hacker should solve like something like 16 puzzle or 18 puzzles before everyone else can solve a single puzzle. So if the cryptocurrency mining network is big, if it's a big network, a lot of miners with powerful mining kits, then no hacker can be 20 times more powerful than that network. Okay, so there is a race condition between the computational capability of the hacker and the computational capability of the entire mining network. Because no one can be more powerful than the entire mining network, Bitcoin is secure. Okay. So what do the miners do? They listen for the transactions, they maintain the blockchain and listen for new blocks. They assemble a candidate block like this 91 here, and they find a solution to that puzzle, which makes that block valid. And you, as the miner, once you find a solution to the puzzle, you announce your solution to the mining network. They check your solution. If it is okay, then it is your block is added to the chain and you get a reward from the mining network. It's like something like $500,000. So it's a big reward, but solving the puzzle is difficult. Okay. So on the one hand, the difficulty of solving the puzzle increases in every 2 weeks. Okay. So this red stepped curve shows the difficulty of solving that puzzle so that a new block can be added to the chain. But on the other hand, the network keeps growing. New people joins the mining network and they keep upgrading their mining kits. So the hardware gets faster and the mining network becomes more powerful, but at the same time, the mining, the puzzle becomes more difficult to solve. Okay, so the mining network increased their computational power from 150,000 something to 100 million something. So a 1,000 times the mining network is now more powerful. Okay, so in the first years of Bitcoin, you could mine with an ordinary computer, but then with graphical processor units, with special mining kits. And now each of this is a special kit, very expensive. Now you can do mining for Bitcoin in like facilities like factories. This resembles to the mining of gold. Okay. So what about quantum blockchain? So these are the last two slides. Sorry for extending this time, but last two slides. Okay, as the quantum computers break the classical cryptography, they break the quantum blockchains as well because the security of blockchains and cryptocurrencies depend on cryptography, classical cryptography. Okay, so quantum computers. So this is a report again published in MIT's Technology Review. This was published in 2017, proving that quantum computers are going to destroy the security of Bitcoin within 10 years, starting from 2017. Okay, so 5 years already passed. In the next year, researchers found that if quantum computers threaten the blockchains, quantum blockchains could be the defense. Okay, so all these communication systems make up the quantum internet, but on the quantum internet, like nodes sharing the entangled pairs, Alice and Bob sharing an entangled pair, now they have a quantum channel. So the application based on this quantum channels and quantum internet could be the quantum blockchain. So the basic idea is to replace the classical computers on the nodes with quantum computers, change the classical communications with quantum communications, okay, and classical cryptography with quantum cryptography. So these three things are the basic three things to replace. And the bad thing about the current puzzle of the Bitcoin is that to make it secure, it must be very difficult to solve the puzzle. And it consumes electricity like crazy, okay? All that mining network consumes electricity more than Norway, more than Argentina, okay? And as more and more people start using Bitcoin for their payments, there will be more transactions to add to the chain, therefore more puzzle to solve. So it would require even more and more electricity, which is terrible for the environment. But in the classical technology, we need it. Otherwise, we cannot make it secure, okay? So for security, we need that effort. We need that electricity consumption. So replacing the existing classical puzzle with the quantum puzzle, therefore replacing classical mining with quantum mining, could be the cure, okay? So it would be not requiring those efforts, therefore not consuming that much electricity, so not terrible for the environment. So it could be sustainable, but yet secure. So that's the end of my presentation. So I can take questions. Actually, I saw some questions already.
Thank you very much, Sensei, for the detailed presentation. Really, it's very informative for everyone, especially those who are in the field. So thank you very much. And
it's my pleasure.
Thank you. And due to the time shortage, so we can answer a few questions. Someone is asking about the PPT, the presentation file. So it's up to Sensei if you can.
Sure, I can share it.
Thank you very much.
Well, this is not, as I said several times, this is not very accurate technically, but this is for non-technical people. Okay, some things are explained just like cartoon. Okay, but it tells the idea. Okay.
Yeah. Okay. So
I will send the PDF of this presentation to you.
Okay, and I can share it with everyone.
Okay. Yes, it's Serizawa-san.
Yes, please.
Okay, there's a question. Which of the engineering disciplines does quantum technology belong, or is it closer to any of the engineering disciplines? Well, as a pure computer scientist, you cannot do that. As a pure electronics engineer, you cannot do that. As a pure quantum physicist, you cannot do that. You need to know computer science, electronics and communication engineering, and quantum physics. Okay, that's why after I started university as a computer science student, I learned that I have to learn quantum mechanics. So I started double minor in physics. And I saw that there are a lot of things in communication, information theory, and coding, a lot of things that they do not teach in computer science. They are taught in electronics engineering. So that when I started master, I said, okay, I should do a master's in electronics engineering, electronics and communication engineering. So this is like a multidisciplinary research. You need to know computer science, algorithms, cryptography, communication engineering, quantum mechanics. So you need to learn a lot, okay? But most of the people in this field are graduate of one major usually, either computer science, mostly from physics, and you just sit and study the other things you need to learn. You learn and you do research, okay?
Great. Thank you, Sensei, for the answer. So does anyone is having another question? Otherwise, we thank you very much for joining the J-MENA activities. Of course, we will try to upload the meeting of today on the J-MENA channel, YouTube channel, so you can watch again the meeting and learn more about quantum computer. I just have one question, Sensei, just to summarize the session. What makes this quantum computer different from the classical one? Just summarize for everyone.
Okay. So just like a river, okay, water flowing, if you take a very small drop or actually a molecule of water, then you can access to its quantum mechanical properties, like taking a single molecule, okay? Or so through the copper wire, okay, we have the electric currents, like billions of electrons are flowing, okay? There is a flow of electrons, billions of them. So that is there's either this flow or no flow. So if you measure its volt, it's like either 0 volts or 5 volts, the digital information on copper wires and transistors. But if you take a single electron, you access to its quantum mechanical properties, which can be 0 and 1 at the same time, and which can be in entanglement. So which can exhibit the superposition and entanglement, so that you can design and implement quantum mechanical algorithms on that, which a classical computer cannot do, okay? Like the superposition. So from mathematics, you might remember that the solution of a quadratic equation gives two results, right? Like x squared plus 3x plus 5. So there are two roots of x, right?
Yes.
Minus b plus or minus square root of delta over 2a. So there are two solutions. A classical computer first finds one solution and then the other solution, because it can perform only one thing at a time, because it can be either this or that at a time. But a quantum bit can be both 0 and 1 at the same time. So a quantum setup can find this solution and this solution at the same time. If there are 100 solutions, classical computer would find each solution one by one, but a quantum computer finds all the solutions at once. But for this, we need to access the quantum world, the subatomic world. We need to be able to manipulate atomic particles like single electron, a single atom, a single proton, single photon, the smallest. Okay, we need to be able to write data there, encode the quantum mechanical dynamics of that atomic particle or the photon, so that it represents our data 0 or 1. And we need to be able to manipulate it so that we can implement our algorithms. And then we need to do readout. Okay, so these are all technological challenges that we are working on. And people like me are developing more on the theoretical side, developing the algorithms, the network circuitry, etc.
Thank you very much, Sensei, for all these details. So thank you very much again. And We appreciate all the members' participation. So due to the short time, we apologize for not answering all the questions, but still you can watch the meeting again and learn more about the field. So thank you, everyone. And we hope to see you soon in the future academic seminars. Don't miss the next Thursday, our academic seminar about renewable energies. Those who are in the field, you are very welcome to join us again. Many thanks.
I just added my email address, and anyone can reach me via email, or you can add me on LinkedIn. Okay.
Thank you very much. Thank you very much, Sensei.
And I see a lot of Turkish people here. I just checked the list of participants. Okay, I'm happy to see a lot of people from my country. Okay, thank you so much for giving me this chance.